So this is a quote from Ramir, who's like a master of complex analysis, right? Nevertheless, there is no canonical, that's probably a misspelling, I think there's only one n canonical, method of finding for a given integrand, and the spelling error is almost certainly mine, for finding for a given integrand an interval of integration, the best path in gamma and c to use. In other words, this technique we're about to learn called contour integration is not something that's algorithmic. It is an art form, right? As Alfors, who's another, like, this is, the book by Alfors is, you know, venerated by a whole generation of mathematicians as being sort of like the greatest complex analysis textbook. I don't use it because it's too hard. Even complete mastery does not guarantee success. Like, I'm just telling you. But these are warnings for if you go past the examples I share with you. We are going to be successful. I'm going to show you the easy examples. What I'm trying to tell you is that if you look and try to understand this method in its entirety, there are many, many things past what I show you, all right? That's all I'm saying. So let's look at the residue theorem. So if we have an isolated singularity, all right, which means that we've got a Laurent expansion, right? Then we can decompose it as this Laurent series. And the coefficients, remember, are given by the integral of, you know, of the circle of radius r that's in the annulus on which the Laurent series converges, somewhere in there, and we divide by 2 pi I, and this. So notice that in particular, if we look at n equals to -1, something super special happens. Namely, this just gives us information about the integral of f itself, right? So if you rewrite this formula, you can rewrite this formula for the integral of f of z over the circle is equal to 2 pi I times a sub -1. That is the most basic form of what we call the residue theorem. And so because the -1 coefficient is so important because of what I just told you, which I'll write down more systematically in a second, so relax. We make a definition that if you have an isolated singularity z0, the Laurent series for that function, then we define the residue at z0 to be the coefficient of the reciprocal term of the Laurent series. So we just pick off the -1 coefficient, just like that. And once we do that, we can use the residue to calculate the integral. I'll do that in a second, but first some residues, so like just some real easy examples. Residue of the reciprocal function at z0 is 1. The residue of 1 over z minus z0 at z is 0, assuming n is not equal to 1. Why? Because 1 over z minus z0 is the Laurent expansion for that function. Right? It's already a Laurent expansion. This over here, we previously proved that z cubed plus z plus 1 over z squared plus 1 is this. All right? So in this animal right here, I can tell you that the residue at I for f of z is 1 over 2i, because that's the coefficient of the 1 over z minus I term. And the residue at minus I is minus 1 over 2i, because that's the coefficient of the 1 over z plus I term, right? Remember, if we're expanding at z0, we're looking for z minus z0 expansions, right? What would the residue be at any other point other than plus or minus I for this function? The answer would be 0. Corresponding to the fact, we know from Cauchy's theorem that the integral around any point except for where the function's singular is 0. If I took a little circle and I surrounded any point except for I and minus I for this f of z, the integral would be 0. So, moving along here, well, I'll save these for next time. I guess I won't. Let me just do things in order. There's not much to say here, really. What all these examples are doing is I've gone through this, like, slog of calculating all these partial fractions decompositions in the previous section, right? So I've got all these formulas, and now I'm just using them and seeing what they mean. So like this partial fractions decomposition shows me clearly that this function is got singularities at 4 and minus 1. And so from this, I can read that the coefficient of 1 over z minus 4 is equal to just 1, see, because the 5's cancel. On the other hand, at minus 1, we get 1/5, right? In order for these calculations to be legitimate, I need to know that everything that's not the reciprocal term is analytic at the singularity. But notice that, like, this 5 over z minus 4 is what? It's holomorphic at 1, right? Because if you plug in 1, you just get minus 3 in the denominator. It's fine. And likewise, this, if we plug in 4, we get 1/5, right? That's holomorphic at 4. So that's how I'm able to know that I can ignore everything except for the place that there's division by 0, essentially. Another way you could read this would be to understand the proof of the partial for every, the proof that every entire meromorphic function on the extended complex plane is a rational function. If you look at that proof, it also showed you that if you have a partial fractions decomposition, then you are looking at the sum of the principal parts of the expansion of the function around the singular points. So like that also says that, it's just another way of saying what I just said. But anyway, this one here, since we have this, we can read off the residue at 0 is minus 1, and the residue at 1 is 1. This has, these terms have nothing to do with the residue. They're reciprocal square. I mean, they're, power 2 and power 3 in the denominator. Only power 1 matters. The sine of z over z to the 6th. We look at it. We do the power series for sine and do the algebra. We get 1 over z to the 5th. Doesn't matter. 1 over minus 1/6 over z cubed. Doesn't matter. This is all that matters. The reciprocal term in z. That is what, by definition, gives us the residue of 1 over 120 in this case. All right. Now, so that brings us to Cauchy's residue theorem. Cauchy's residue theorem simply says the following. If you have D a bounded domain in the complex plane with a piecewise smooth boundary, partial D, and you suppose F is analytic on D and its boundary except for a finite number, I've isolated singularities, Z1 through Zm, then the integral around the boundary is simply 2 pi I times the sum of the residues. So the proof, like a proof I could give you is if the picture looks like this, right? And let me just talk about the deformation proof that I kind of sketched in the thing. If you could imagine having like a little circle around each one of these, right? Then if you can imagine that little circle, outside of that little circle and inside of the domain D, the function is holomorphic between those circles and the edge, because the only place that the function's not holomorphic is at these isolated singularities, right? So the deformation theorem said that the integral from like one region to another that you can form by like deforming it. In this case, you can imagine taking the little bubbles and like blowing them up to get to the outside shape, right? If you do that in such a way that the bubbles don't overlap. But maybe the bubbles actually become these pictured regions that I have here, right? You could envision it that way. Well, then the deformation theorem said that if the function is holomorphic between the region 1, which deforms to region 2, then the integral around the inside region is equal to the integral over the deformed region. But the integral around little circles, like around Z1 encircling Z2 encircling Z3, those are easy to calculate because the only thing that contributes to the integral here, right, by the Laurent expansion formula I looked at about 10 minutes ago, is just the -1 coefficient of the Laurent expansion around Z1. So the integral around a little circle here is 2 pi I times the residue of Z1. Encircling this with a little circle, the integral around this one is 2 pi I times the residue at Z2, 2 pi I times residue at Z3, 2 pi I times residue at Z4, and 2 pi, and so forth. And when you add them all together, you get exactly that. So this is, but it rests, guys, it rests on this formula back here that we went over. this right here, when we put minus 1, so 2 pi I times a minus 1 is equal to the integral around z minus z naught, the circle of radius r of this contraption right here, which just becomes f of z in n equals minus 1 case, right? Remember what this is. This is a little circle that encircles the singularity at z naught. So I'm thinking of that little circle around each of the finite singularities, the isolated singularities in the residue theorem, in that way. That's how I know it's 2 pi I times the residue. It's that. Oops. So this is very, very powerful as a theorem, and it becomes more powerful once we learn. There's 4 rules that help calculating residues that we need to go over. So I'm tempted to do them at the moment. I don't know if I quite have enough time for it, though. Yes, I do. Rats. Well, we'll look at the rules. Rule number 1. If f of z has a simple pole at z naught, then you can calculate the residue by taking the limit as z goes to z naught of z minus z naught times f of z. So since f has a simple pole, that means that we have this formula, right? Where g of z is analytic at z naught. And so if we take the limit of this times that, well, then the z naughts be canceling, and it leaves us a minus 1, z minus z naught g of z. But of course, the limit as z goes to z naught makes this 0, which just leaves us a minus 1. So this is rule number 1. Here's how it's put into practice. Like this right here would be a pain to calculate the Laurent expansion at I, right? But we don't need to do that. It's also fairly clear that it's a pole of order 1, because if you factor this, you just get a z minus I, z plus I, right? So we know it's a pole of order 1. So all we have to do is multiply this by z minus I, factor the denominator, cancel those. That leaves us with this. We take the limit as z goes to I, which just amounts to plugging I in, like so, 1 over 2I. There you go. That's the residue. So rather than going through the other rules for you today, we'll settle for rule number 1. There's 4 rules that you need to learn. Let me actually make an example and show you what we can do with this. All right? Like suppose you were integrating z cubed plus z plus 1 over z squared plus 1 dz, right? Over, say, modulus of z minus I equals to 1. All right? Is this my example 7? Example 8? All right, our final example for today. So what's that circle look like? It's got a center at I, right? And it's got radius 1, so this is the circle that we're talking about. And we're going to take it to be counterclockwise oriented, all right? That's by default our convention, all right? Can you guys calculate the integral? So where are the singularities for this function? There's one at I, right? There's also one down here at minus I. Minus I is not inside the loop. We don't care about that. The residue theorem says that the answer is 2 pi I times the residue of the function at I. I'm calling this whole thing f of z, all right? But we just calculated that to be what? 1 over 2i. So this is 2 pi I times 1 over 2i, also known as pi. There you go. We just integrated that complex function. Trust me when I tell you this would be harder if we tried to do it from the definition. Right? It would be bad. This is the power of the residue theorem. But, so yes, we can do these kinds of complex integrals, but as over the next few lectures, I'm going to show you how we can use this power to calculate all kinds of improper integrals that were before nearly impossible to do with calculus 2 methods. That's probably not true. Probably all the ones we're going to do, there's probably some sort of elite calculus 2 chicanery which would take care of them. But those things are not known to you, so I can just say that you can't do them with calculus 2 and leave it at that.